Good day, grade 9. We are back for another episode of Learning. Again, I am Sir Roy, your science teacher, and for today, we're going to talk about the structural characteristics of carbon. The most essential learning competency that will be covered for our lesson today is to explain how the structure of the carbon atom affects the type of bond it forms. So let's begin. Carbon isn't a difficult element to spot in your daily life. For instance, if you have used a pencil, you've seen carbon in its graphite form. Similarly, the charcoal pieces of your barbecue are made out of carbon, and even diamonds in a ring or a necklace are a form of carbon. What you may not realize though is that about 18% of your body weight is also made of carbon. In fact, carbon atoms make up the backbone of many important molecules in your body, including proteins, DNA, RNA, sugars, and fats. Let's talk about the element carbon. As you can see in the illustration, carbon is represented by the symbol C. It is a nonmetal. It has an atomic number of 6. Therefore, it has 6 protons, 6 neutrons, and obviously 6 electrons. There is a particular branch of science that deals with the chemistry of organic compounds, and that is what we call as organic chemistry. Now let's talk about the history and uses of the element carbon. Carbon was first discovered as charcoal in the prehistoric times. It is considered as the sixth most abundant element in the universe. As you can see in the illustration, there are three naturally occurring allotropes of carbon, which are amorphous carbon, the graphite, and the diamond. These are the so-called allotropes of carbon. Let us talk about them one by one. The first one is the amorphous carbon. It is formed when a material containing carbon is burned without enough oxygen for it to burn completely. This black soot, also known as the lamp black, the gas black, channel black, or the carbon black, is used to make inks, paints, and rubber products. It can also be pressed into shapes and is used to form the cores of most dry cell batteries, among other things. I have here the illustration of a amorphous carbon. It is an allotrope of carbon that does not have any crystalline structure. As you can see, this type of carbon has no definite shape or definite arrangement of elements or atoms. Now, let's talk about the graphite. Graphite is one of the softest material known. It is a form of carbon that is primarily used as a lubricant. As you can see on the illustration, although it does not occur naturally, most commercial graphite is produced by treating petroleum coke, a black tar residue remaining after the refinement of crude oil in an oxygen-free oven. Naturally occurring graphite occurs in two forms. It could either be an alpha or a beta graphite. These two forms have identical physical properties but they have different crystal structures, just like shown in the picture. As you can see, they have the alpha and the beta graphite have different crystal structure. Now, the pencil that we are using, although the black one or the black material used in pencils are known as lead, it is actually called as the graphite. How about the diamond? The third naturally occurring form of carbon is one of the hardest substances known. Although Naturally occurring diamond is typically used for jewelry. Most commercially quality diamonds are artificially produced. These small diamonds are made by squeezing graphite under high temperatures and pressure for several days or weeks, and are primarily used to make things like diamond tip saw blades. This is an illustration of a diamond, and this is the illustration of the arrangement of atoms in a diamond. The word diamonds comes from the Greek word adamas, which means unconquerable and indestructible. Diamond is one of the hardest mineral on earth, and it is only diamond which can scratch another diamond. We also have here carbon 14. It is a radioactive isotope of carbon with a half-life of 5,730 years. It is used to find the age of formerly living things through a process known as radiocarbon dating, just like what is being shown in the illustration. Now, there are several known carbon compounds. These are carbon dioxide or CO2, the gas that we exhale. We also have carbon monoxide or CO, carbon disulfide or CS2, chloroform or CHCl3. We also have carbon tetrachloride or CCl4, methane or CH4, the gas being produced from garbages. We have acetylene or C2H2, benzene C6H6, acetic acid CH3COOH, the one that's component of vinegar, ethyl alcohol C2H5OH, and we also have ethylene or C2H4. Why carbon is cool? Each carbon molecule has four unpaired electrons in its outer energy cell. Therefore, carbon atoms can form covalent bonds with up to four other atoms, including other carbon atoms. As you can see in the illustration, here the carbon atom is bonded to four hydrogen atoms. The red dot represents the electron from the hydrogen, and the blue dot represents the electron from the carbon. Carbon-based molecules have three fundamental structures: the straight chains, the branch chains, and the rings, just like what is shown in the picture. So we have here the straight, which shows a linear illustration of carbon atoms. We also have here the branches. From a linear structure, there are several branches. And we also have here the ring, which is a closed figure of carbon atoms. Then we also have the term allotrope. Allotropy is a behavior exhibited by certain chemical elements. These elements can exist in two or more different forms known as allotropes of that element. When an element exists in more than one crystalline form, those forms are called allotropes. And carbon has different allotropes, just like what is being shown in the picture. Letter A, it is known to be the structure of the diamond. Letter B, that is the structure of the graphite. Letter C, structure of the lance-delight. For letter D, that is the structure of carbon-60. Letter E, that is the structure of C, carbon-540. Letter F, that is the structure of carbon-70. Letter G, that is an example of the structure of amorphous carbon. And letter H, that is the structure of carbon nanotube. Now let us compare diamond and graphite as an allotrope of carbon. So as you can see in the illustration, diamond is transparent and has no color. On the other hand, graphite is opaque and black. Diamond is the hardest substance known to man. Graphite is soft and spongy in texture. Now, diamond cannot conduct electricity at all. On the other hand, graphite is a very good conductor of electricity. Both allotropic elements are solid. They are non-gaseous. Also, both diamond and graphite are insoluble in water. Now let's talk about the Lewis dot structure. The Lewis structure are diagrams that represent the valence electrons of the atoms within a molecule, just like being shown in the illustration. Carbon, therefore, forms for two electron bond to other atoms, which may be single, one shared pair, double, two shared pairs, or triple. Mean to say three shared pairs. How about the carbon chains? Carbon chains from the skeletons of most organic molecules. Carbon chains also vary in length and shape. Look at letter A. In terms of length, if we're going to compare ethane and propane, propane is longer compared to that of ethane because there are 3 carbon atoms present in propane while in ethane there are only 2. In terms of letter B, when we speak of the branching aspect, 2-methyl propane is longer or there are more branches compared to that of butane. Letter C, we have here double bond position. So 1 butene and 2 butene. They are different in such a way that the double bond location is different in the two compounds. For letter D, we have the presence of rings. We have here the cyclohexane, hexane, and the benzene. In cyclohexane, there is only a single bond that forms the ring. On the other hand, in the benzene structure, you would see here that in the ring structure, there are some double bond present. How about the straight chain alkanes? The general formula for an alkane is CnH2n plus 2, where N is the number of carbon atoms in the molecule. So how are we going to get the molecular formula of a carbon or alkane using the formula? For example, if the given N is 4, by using the formula CnH2n plus 2, let us substitute 4 for the value of N. Therefore, we can have C4H2 times 4 plus 2. In order to solve that, let us first have this one, C4H8. We arrive at 8 because we multiply 2 times 4. So, adding it to 2. Simplifying the equation, we have C4H10. That is how we get the molecular formula of alkanes. This is a table summarizing the carbon name of the different alkanes from carbon containing 1 up to 10 numbers. Now, let us check if you have learned something from our lesson for today. For this particular exercise, determine what kind of carbon allotropes are the given pictures below based on its different structural modification. Let us have number 1. What allotrope is this? This is carbon 70. How about number 2? It is carbon 60. Then number 3. This one is Lonsdaleite. For number 4, this is an allotrope known as graphite. Number 5, this one is known as the structure of the diamond. And number 6, this is amorphous carbon. Very good. Let us move on to another set of exercise. Given the value of N, write the names and molecular formulas of straight chain alkanes. So again, following the general formula CnH2n plus 2, there are given value of N, you have to identify the name and the molecular formula. Let's have number 1. If N is equal to 2, what would be the name and the molecular formula? The answer is ethane and C2H6. For number 2, if N is equal to 4, the name would be butane, and the molecular formula is C4H10. For number 3, if N is equal to 5, the name will be pentane, with a molecular formula of C5H12. For number 4, if N is equal to 7, the chemical name would be heptane, and the molecular formula is C7H16. And for the last number, if N is equal to 9, the name would be nonane, and the molecular formula is C9H20. That ends our lesson for today. This is the reference that I made use for this presentation. Thank you for watching, and don't forget to subscribe in my YouTube channel for more videos.